All right, now we're going to simplify radicals that have higher root indices. What we mean by that is, normally when we write the radical of x, there's actually an n that goes right here. Now that n is the index. That tells us how many exponents we need to get out of the radical. Normally, for example, when we have the square root of 9, the index in this case is actually a 2, but we don't actually write the 2 in there usually. It's just sort of implied. So when it's missing, that means the second root, or the square root. We just get the square root of 9 is 3. We're now going to deal with what if we have higher indices. So, for example, when we have the square root of a squared, that gives us just a. Now, if we change the index and we say, now what if the index is 3, the cube root of a to the third power, that also is just going to give us a. The index and the exponent have to match to be able to get out of the radical like that. Let's keep going with it. Let's take the fourth root of a to the fourth power. And that's going to give us just a, because the index and the exponent match. Let's do a generic now, and we're going to do the nth root of a raised to the nth power. That again is just going to give us a. As long as the exponent matches the index, we're good to go. Let's start off with this example. We're going to do the cube root of 1. Well, 1 is really nice because we can rewrite it as the cube root of 1 to the third power, which just gives us 1. Let's try another example. We'll get crazy and use a fraction here. We're going to do the cube root of 27 over 64. Now, we're going to have to do some prime factorization here, but that's okay. The cube root, 27 just becomes 3 raised to the third power. 64 becomes 4 raised to the third power. So again, the exponents and the indices cancel one another out, and we just get nicely 3 over 4, or 3/4. Let's make it generic now and use a letter. We'll do the third root of x raised to the 6th power. Well, I can break that up now, but I need to break it up into perfect cubes now. So x to the 6th power becomes x to the third power times x to the third power. Now, each of those x's gets to come out. So I end up with just x times x. Both are out of the radical, so I end up just with x squared. Now, there's an odd rule that says when the index is even, like 2, 4, 6, 8, we have to have a positive value under the radical, otherwise we end up with what's called a complex number. We're trying to avoid those right now. If it's an odd index, then we can have a positive or a negative under the radical. The reason for that is when we raise a number to an even power, we always end up with a positive value. But when we raise a number up to an odd value, we can get an even, or a positive or a negative value. Both are acceptable. Let's see what we mean by this. This next example, we're going to end up with the fifth root of negative 32. Now if we look at our rule over there, this is an odd value, so we can have a radical under the negative. This becomes the fifth root of, in parentheses, I'm going to put negative 2 raised to the fifth power. And if you multiply negative 2 in 5 times, you will end up with negative 32. Notice the index and the exponent match, so my final answer is negative 2. I know it seems weird to have a radical and get a negative value at the end, but when you have an odd index, that's very possible to do. Let's try this next one. This time we're going to have the fourth root of negative 16. Now here we have a problem. If we look at the rule right above, if I have an even index, I cannot have a negative number under the radical. So in this case, we're just going to stop and say that this is not a real number. In fact, to even simplify this one further, we have to use a branch of math called trigonometry, which gets a little complicated. All right, our last example is going to be a big one. We're going to do the fifth root of 32, x to the 12th, y to the 24th. Now my goal is I want to break it down into as many exponents of fifth power that I can. So I'm going to end up with the fifth root. 32 breaks down into 2 raised to the fifth power. You can prime factorize that on your own. X to the 12th power becomes x squared times x to the fifth times x to the fifth. Now you notice if you add up all those exponents, you're going to get x to the 12th back. But I deliberately want to break this up into perfect fifth powers. Y to the 24th is going to get a little tricky as well. That's going to give me y to the 4th times y to the 5th times y to the 5th times y to the 5th, and one more, so I have 4 of those. Again, note, if I add up all of those exponents on the y's, I better get 24 back, and I do. Now, I'm going to notice here that all of the fifth power ones all get to come out, including the x, and 4 of the y's. So I end up with 2 times x times y 4 times. Notice their exponents are gone. Inside, I'm still left with the fifth root of x to the second power, y to the 4th. They didn't have enough exponents to come out, so they have to stay inside. Simplifying this up, I end up with 2 x squared y to the 4th times the fifth root of x squared y to the 4th. Ooh, you may need to go through that one again. That one's a little complicated.